So projectile motion is of course in extension 1, but it does appear in extension 2 as well, and other things can be put into the problem. This first one here, a stone's thrown so it'll hit a bird at the top of a pole. So a bird sitting on the top of a pole. However, as soon as I throw that stone, the bird flies away at a speed of 10 meters per second, but you see it's a really stupid bird. The stone will end up reaching height double that of the pole, and then when it comes down it hits the bird anyway. The reason I say it's a stupid bird is the bird should have flown towards me, not away from me, and then it wouldn't have got hit. Find the horizontal component of the stone. There's no resistance in this problem, we're assuming that, so I know the projectile will basically describe a parabola when I throw it. And this is where, in this sort of question, knowledge of quadratics is going to be a more efficient way of solving this than actually using calculus. I know the greatest height will occur at the vertex of the parabola, so I'm going to let the coordinates of that vertex be 0 to h. So twice the height of the pole, and basically I'm setting the origin directly under the vertex of my parabola. So therefore I know the equation of the parabola will be in that form. It'll be 2h minus some constant times x squared. I know that. There's my picture. There's the curve. And I've added in the pole there. It's of height h, and the bird starts flying to the right. Let's find the x coordinate of the pole. So when y equals h, h will be 2h minus kx squared. I can play around with that, and I get that it's plus or minus root h on k. Well, this one must be minus root h on k. The one on the other side would be the positive. So now we can work out how far the bird flies before it gets hit. It's going to be twice that, twice root h on k, and we know it's travelling at 10 meters per second. So I now know how long the bird flies for before it's hit. Speed equals distance over time, rearranging that, time equals distance over speed. So it's 1/5 root h on k. Let's find these x-intercepts. So when y equals 0, and I now have the x-intercepts. So I know the starting point. So that's where I'm throwing the stone from. I now know horizontally how far the rock travels. I'll add that to the root h on k, and that's how far the rock travels. Again, let's work out the speed of the rock, because I think that was what we were asked to find, wasn't it? Let me just go back to the actual question. Find the horizontal component of the velocity. This is what we want to find. Again, speed equals distance over time. But we now know the distance, we just worked out the time, I can get the speed. 5 outside of root 2 plus 1 meters per second. So using my knowledge of quadratics, didn't use one bit of calculus to solve the problem. But what else could happen in extension 2 is that now we know about resisted motion. So it's possible we could consider air resistance. Now this first one doesn't, but I'll use this as our first example. It's a 2021 paper, projected. It's basically just our standard projectile motion question, you see. And they've given us the displacement vector, so we don't have to go and work it out. Saves us a bit of time. We've got the equations we can play with. Now we're told that for some values of theta, there's going to be 2 times when the particle's position vector is perpendicular to its velocity vector. Find those values of theta and also justify that both of those times will occur during the time of flight. They gave me the displacement vector. Well, if I differentiate each component, I'll get the velocity vector. There it is. We've been told that they're going to be perpendicular. Well, dot product is equal to 0. Whoa, nice little equation there. Okay, tie these up a little bit. I've got this cubic in terms of t. But what I do know is t is going to be a positive number. It's not going to be 0. So actually I could divide everything by t and it's not going to be a problem. I'm not going to divide out a solution. T can't equal 0. So g squared t squared minus 3 gut sine theta plus 2u squared, at least it's a quadratic, and whilst I might struggle to factorise that, What I do know is that if the discriminant of that is greater than 0, there will be 2 solutions, and we've been told there are 2 times. Therefore, there must be 2 solutions. I know the discriminant of that is greater than 0. Sine squared theta ends up being greater than 8/9, which means it must be between 8/9 and 1, because theta is going to be acute. It's a projectile motion question. So sine theta ends up being positive, or sine squared obviously has to be positive, but sine theta ends up being positive as well. So we now know sine theta is in between the square root of 8/9 and 1. So the angle is in between 71 degrees approximately and 90 degrees. That's the range of values. But now we have to show that actually that will happen whilst it is in the time of flight. So when does it hit the ground? What is the time of flight? So when y equals 0, I want to solve that component is equal to 0. So the time of flight will be 2u sine theta over g. Both values of theta must occur when t is in between those values for it to occur in the time of flight. Let's go and solve that quadratic we got before and find the values of t. We want to show that, yeah, it will be between these 2 values. I've got 3u sine theta plus u, okay. I know that 3u sine theta minus u times the square root of 9 sine squared theta minus 8 must be bigger than 3u sine theta minus u the square root of 9 sine squared theta. So I do know both times are greater than 0. Because clearly if I add this on, it's going to be positive. But what I'm now saying is, well, if I subtract it, it's going to be greater than 0 as well. Is that right? Because the right hand, I mean, I didn't write it down, but clearly the right-hand side, this square root of 9 sine squared theta is 3 sine theta. So we get 0 for the right-hand side. I know it's a positive number. Okay, I know they're both positive. But what about the larger value then? Because remember, yes, they've got to be positive, but they can't go bigger than 2u sine theta on g. So what is the greater value? The greater value would be when we're adding that on. But again, I'm going to play with an inequality here. What I'm saying is, well, 9 sine squared theta minus 8, I know sine squared theta is less than or equal to 1, so therefore, that expression must be less than or equal to 9 sine squared theta minus 8 sine squared theta. Well, what do you know? That turns out to be 2u sine theta on g. So yes, both of those times will occur during the time of flight. And so, all right, those angles are acceptable. 71 to 90, in that range, will solve our problem. As I say, a little bit more involved than an extension 1 projectile motion question. How about this one then? Particle of mass 1 kilogram, that makes life easy because unit mass is beautiful. With speed 40 metres per second, angle of 30 degrees to the horizontal plane. So we've got our projectile motion, but use that information to show the initial velocity, and they've written it as a vector, so 20 root 3 horizontally, 20 vertically. Well, that one really is no different to what we do in 3. We're just working out the initial conditions. So, okay, there you go. There's the horizontal velocity initially. There's the vertical. So yes, I've shown the initial conditions are indeed that. Forces acting on the particle, yes, are gravity, but now we're going to include air resistance. And the air resistance is proportional to the velocity with a constant of proportionality 4. And to make life easy for ourselves, they've let the acceleration due to gravity be a nice round 10. The position vector of the particle at time t seconds is rt, the position vector, and velocity vt. Okay, just standard notation there. Show that the velocity vector is that expression there. Start by drawing force diagrams, is what I'm saying. Even for what might look like the most simplest question, this one deserves a force diagram just to make sure we get this. So horizontally, when I'm playing with projectile motion and vectors, if I'm differentiating down, I'll leave it in vector form. I don't have a problem with that because that's nice and easy. But when I'm integrating up, I will always break it into 2 components because it can get real messy trying to keep that all inside one vector, the actual setting out and what have you. Let's look at it horizontally. We have resistance now. So we have 4 x dot in the negative direction. Vertically, yeah, we have our force due to gravity, but it also has resistance, or y in the negative direction. On the left hand side, I get acceleration is minus 4 times the velocity. On the right hand side, I get the y acceleration is minus 4y dot minus 10. I'm going to have to integrate both of these to get the two components. Left hand side, dx dot to t, separate out the variables, sub in the initial conditions that we just worked out, and great. That's what they wanted for the horizontal component. We got that. Now let's do the right hand side. Again, separate out, substitute in those initial conditions we just worked out, and excellent. We get that. And now I'll say, well, righto, yes, as a vector, I could write it like that. Now we've got to go and find the displacement vector. Okay, so again, I will treat them separately. I'll work out the components individually. So dx to t, separate out the variables. Initially I'm at the origin, so 0, 0. And yes, that matches what I want. Now I'll do the vertical one, and again, substitute in our initial conditions of integration and playing around with it so I can get it into the form that they wanted. But yes, I can confirm that is our displacement vector. But this was the interesting part of the problem. They gave us this graph, or two graphs. One's y minus e to the power of minus 4x, and the other is y equals 4x on 9. Using the diagram, find the horizontal range of the particle. When does it hit the ground? I've written it like this, but essentially we're saying, oh, well, that's when the y component is equal to 0. It's going to hit the ground. So let's go and solve that. And I end up with this. And that's where the graph now comes in, because they've told me the point of intersection of those two on the graph. It's when x0 is 2.25, so the solution to this is just 2.25. Well, approximately. That tells me the time. Now I'll go and substitute it into the x component to go and work out the range. So 8.659185278, approximately. They said to one decimal place, all right, 8.7 meters. Okay, so 6F and 6G